Good morning, good afternoon, everyone. I'm Laura Darby, working as marketing manager at Energypool. So thank you for joining us for this first Energypool webinar about microgrids and hybrid power plants. We will have today a specific focus on projects taking place in Southeast Asia and on the value creation made from Energypool optimization platform. So today we will hear a presentation from 3 speakers all working at Energypool. First of all, Jean-Pierre, head of the software business unit. Jean-Pierre will give us a global overview of Energypool solutions and our view on microgrids development. Then Nicolas, as software solution engagement manager, will present the economic optimization of a connected microgrid in Thailand. Finally, Jean, PhD and Business Development Manager at Energypool, will close this presentation session with a focus on high-landed hybrid power plant control for reliability. We will close the webinar with a 15-minute Q&A session. So please use the chat window to send your question to our speakers. Let's start with a brief introduction about Energypool. Energypool is a smart energy manager of complex systems covering activities such as demand response aggregation, which is our historical core business, consisting in monetizing flexibility in electricity consumption from C&I end users. In addition to demand side, Energypool also manages and optimizes a wide range of distributed energy resources, including microgrids. Energypool activity did start in France about 10 years ago, back in 2009, and we are now developing business activities in about 10 countries and working in partnership with C&I clients, TSOs, utilities, and microgrid project developers worldwide. As Smart Energy Manager and Energy Transition Enabler, we address key needs from energy market players through consulting, technology, and operation management services. During this webinar, we will especially focus on Energypool software and solutions offer. Well, that's all for this short introduction. Jean-Pierre, may I ask you to continue, please? The floor is yours.
Energypool is addressing all the components described here through services, operation, or via our software platform. Our platform is addressing all types of generation assets, whether they are dispatchable or not, all end user segments, and all types of storage assets with the different maturity level depending on the technology, of course. Depending on the service delivered, our customers are either renewable developers or operators. They can be utilities who operate generation assets and sell power to consumers. In that case, we are generally in a virtual power plant business case. They can be grid operators who are buying flexibilities to balance the grid. End users, generally large industrial customers, and microgrid or hybrid power plant operators. And when they exist, we interact with power markets, flexibility markets, and peer-to-peer trading platforms. We mention here the name of INOplus. INOplus is an IT company based in Bangkok, and we developed with them recently an integrated solution addressing demand response and peer-to-peer trading with blockchain in Thailand. This is an overview of our software platform. This platform was initially developed to support Energypool's own operation, and it is now widely used by our external customers. We are proud to count in the list of customers TEPCO, the main power utility of Japan. TEPCO has been using our platform for more than 5 years now to manage several hundreds of end users and distributed generation assets. They have been extremely demanding since the beginning of our collaboration, which allowed us, well, I should say, which pushed us to raise the level of performance and reliability of our solution. Energy Pool has been investing intensively in R&D for the past 12 years, and we keep investing in the continuous improvement of this software solution. The solution is built on top of an industrialized, robust, and scalable cloud platform. And the key features available are first, forecasting. We do forecasts based on machine learning infrastructure, and we deliver forecasts for generation, consumption, and market prices. The second key feature is aggregation and optimization of all types of assets, loads, distributed generation, and storage assets. We also have monitoring and control of all types of assets. This is based on a secured and scalable IoT infrastructure, and we connect the assets through a wide range of devices ranging from basic and low-cost gateways to microgrid controllers. The platform also offers a wide connectivity to TSO, DSO utility systems, to third-party service provider platform, like weather forecast services, to market platforms and back-office systems for invoicing, for instance. And the solution allows to deliver different types of services. We mentioned here power flex operation. This is actually demand response. And we are covering primary, secondary, and tertiary reserves. And we deliver through this platform energy optimization in different contexts. Can be the optimization of a portfolio of assets, which can be a mix of demand, generation, and storage. Can be in a hybrid power plants context, and of course, microgrid context. We know there are several definitions of microgrids, but we propose here a generic one. Microgrid is typically a mix of distributed energy resources, which can be renewables, fossil, or batteries. It contains also loads, which can be classified in 3 categories. Critical loads, for which we need to ensure the continuity of power supply. Non-critical loads, which can be switched off in case of an issue. And controllable loads, typically HVAC, for which we can increase or reduce the consumption, at least temporarily. We also see coming into the picture new types of assets like EV charging infrastructure, which introduce new usages. And of course, a microgrid has sometimes, not always, a connection to the main grid and can be connected or disconnected temporarily or permanently with the grid. The main drivers for microgrid developments are service continuity, access to energy. The figure we put here represents the share of worldwide population who does not have access to electricity. The reduction of grid losses, the reduction of energy cost, the increase of renewable shares, and the reduction of CO2 emissions. Let's look now at our solution for microgrids and hybrid power plants. The solution combines a local microgrid controller and a cloud platform. The role of the local microgrid controller is to optimize in real time the assets of the microgrid and to keep the frequency and voltage within acceptable limits when the microgrid is in islanded mode. And on top of the microgrid controller, the cloud platform brings additional capabilities like long-term data storage, displays and dashboards, and the most important ones that we will develop in this presentation, forecasting services and forward-looking optimization. The solution is tolerant to temporary internet connection losses. The local microgrid controller can keep running autonomously with no connection with the cloud platform, but in that case, forecasting and forward-looking optimization are not available. I will not go into more details here. I will let Nicolas and Jean further develop the benefits of forecasting and forward-looking optimization in the context of microgrids. We just wanted to highlight here a few facts regarding microgrids. On the left-hand side, the chart shows that Asia Pacific accounts for 30% of the total microgrid power capacity installed worldwide. These figures are 2020 figures. And on the right, we have highlighted the top 5 value propositions, which are renewable energy integration, resiliency, cost savings, reduction of CO2, and reliability. This graph comes from a study that was made in 2019 by Guidehouse Insights. And the global ranking are illustrated by the green bars, and there is a focus on US and California, which are represented by the red and blue bars. I hand it over to Nicolas for the deep dive into forward-looking optimization.
Thank you, Jean-Pierre. I'm taking control of the presentation.
I give you the control.
Thank you. Thank you, Jean-Pierre. And hi, everyone. I hope everyone can hear me properly. Today's first business case is an application of forward-looking optimization onto the operations of a microgrid in Thailand. So in the first part of this presentation, we're going to introduce the concept of forward-looking optimization. And in the second part, we will see how it is applied for the operation of this microgrid in Thailand. Okay, so if we take a look back at this global overview that Jean-Pierre was showing before, showing the energy pool solution, we can see the 2 levels Jean-Pierre touched upon, which are the microgrid controller and the cloud platform. And if we focus rapidly on the microgrid controller, of course, it is a very important part of the system since it is responsible for maintaining grid stability. But what we can say about the way it works is that it's real-time control, taking instantaneous reactions to real-time conditions on the microgrid. So if you like, it does have a myopic view of the way the microgrid operates. Excuse me. Here we go. Things that the microgrid controller does not account for are information about the near future. For instance, here we have illustrated, excuse me, this. Okay, here we go. We have illustrated, let's say we are positioned around the now arrow. The microgrid is busily trying to operate the microgrid. It's not going to really worry much about, for instance, what PV production might look like for the rest of the day. And this is just an illustration, but there are other information about the future that the microgrid controller does not account for when it's trying to maintain stability on the grid. Another thing that the microgrid is not necessarily taking into account is, or not doing, is taking proactive actions when it's trying to control the grid. There are some actions that can be delayed or anticipated based on what might happen or conditions in the near future. And here again, we have illustrated the fact that it is possible, for instance, on this little example, that we might want to discharge a battery earlier on so that we are able later on, we have the available capacity to charge it again to avoid wasting PV generation. So those things are exactly what forward-looking optimization does. It considers the next foreseeable future, the next few hours in the foreseeable future, accounts for a lot of information that is available and that can be computed, and then plans or operates the grid with proactive actions to better optimize it. So how is this done? So here again, we've got another representation of the system with the microgrid on the right. As you would expect, the microgrid controller monitors continuously the microgrid assets, and that allows it to, of course, do the real-time control of the assets to maintain stability on the microgrid. But it's also sending some of the information up to the cloud platform, where regularly, at regular intervals, the forecast module is triggered to produce, using information from the microgrid controller and possibly information from external sources, to produce forecasts, to forecast information about the short-term future. And then this, in turn, is used by the forward-looking optimization module, together with, again, information that might be coming from external sources, to compute operation programs for the set of assets in the microgrid. So those programs are profiles, if you like, of what to do for the next few hours. And those profiles are sent to the microgrid controller, so like I said, at regular intervals, say hourly, for instance. And then the microgrid controller uses those programs, or the most recently received programs, as guidelines to operate or to control the assets on the grid. So in fact, we are adding a dimension of information to the microgrid controller. It's not just instantaneous real-time information from the microgrid. It's also short-term programs, optimized programs for the operation of the assets. So let's take a look at this last step of the process, which is how the microgrid controller makes use of the programs that are computed at regular intervals by the cloud platform. So let's say we are a bit before 7 in the morning, where this blue now arrow is. And let's assume that the platform has computed programs for a set of assets. So that's what's represented by the with the graph. And that those programs have been sent to the controller. So let's assume now that time has progressed, and that we are at some stage between 7 and 8 in the morning, which is that blue represented by that vertical blue line on the new graph. And what the microgrid controller does is it takes that first hour from 7 to 8 of those latest programs that were sent by the cloud platform. So the programs are indicated by solid lines on the graph. And it's trying to align, in the way it's controlling the assets, it's trying to align with those targets calculated by the platform. But of course, those targets were computed based on forecasts, so they're just ideal, theoretical ideal targets. So the controller continuously adapts around those targets because it monitors, of course, the assets. So that's what's represented by the dotted lines, and you can see the deltas. So it continuously adapts to absorb those deltas between forecast-based optimals and real-life conditions. And so this is a process that's going to be repeated at regular intervals, like I said before. When the time will be approaching 8 o'clock in the morning, the microgrid controller should receive an updated program from the platform. And then the microgrid controller will move on to those new programs to operate for the time between 8 and 9. So the important message to keep in mind is that the cloud platform computes those ideal theoretical targets that are based on a more global view of the operation of the microgrid over the next few hours, typically 24 to 48. And then the microgrid controller takes those as guidelines, and it tries to operate the assets around those but still making sure, of course, that the stability is maintained on the grid, the microgrid. So I'm a bit stuck now. I can't move on to the next slide. Okay, here we go. So now we're going to take a look at how this forward-looking optimization concept is used in Thailand to operate a microgrid. The main objective of this project is to ensure power supply on the school campus while minimizing the cost of energy. So the school campus contains 8 buildings. Some are considered to be critical load, and some others are non-critical load. There are 7 sets of PV panels, including panels that are coupled with batteries. There are also 2 sets of large batteries of different technologies. In the buildings, there is also some load that's considered flexible. That's the energy consumed by air conditioners. Also, an important point of that microgrid is that it is connected to the national main grid, and it can exchange electricity, import or export electricity with this main grid. And when it does so, it is at spot price. And for information, this spot price is a simulated spot price because, as some of you might know, there is no spot price in Thailand yet. But on this project, the client wants to simulate a spot price to anticipate or estimate the impact of such a spot price when it comes, when the market is open to deregulation. Another aspect of the microgrid is that it can actually disconnect from the main grid if the state of the main grid is considered unstable. So there is an islanded mode that's possible. Technically, there is one microgrid controller that's connected to all the assets on the microgrid through a local area network. And lastly, on this project, the Energy Pools EMS is in charge of managing the connection and disconnection with the main grid. When the microgrid is disconnected, the system is in charge of doing the usual real-time optimize or real-time controlling of the assets to maintain grid stability. And when the microgrid is connected to the main grid, it's in charge of forward-looking optimization to optimize, to economically optimize the cost of energy. So in details, what is the forward-looking optimization doing on this project? So each hour, the forward-looking optimization is computed. So it's on this project, it's computed hourly. And each hour, the objective of the forward-looking optimization is to reduce energy costs. And it's got several things to play with to do that. One is to maximize the net revenues it's getting from exchanges with the main grid. We talked about this before, selling and buying at spot price. Of course, it's trying to maximize the use of PV generation, trying to optimally time the charging and discharging of batteries, and also trying to optimally plan or control air conditioning depending on the evolution of the spot price. It's also accounting for, of course, the topology of the microgrid, and it's accounting for some information about the future we talked about. So spot prices, PV generation forecasts, and forecast of non-flexible demand. And it's also accounting, of course, for the relation between HVAC consumption and the temperature in the buildings. It's also making sure that a lot of constraints are satisfied. There's a global, at the scale of the whole microgrid, a global power balance, but there's also some local congestion points that are implemented in the optimization. It's also making sure that some of the constraints that battery suppliers are recommending are satisfied. And finally, of course, it's making sure that temperatures in buildings are within acceptable limits. And then each hour, it produces those 24-hour ahead programs that indicate the profiles that the assets should be following, that their set points should be following for the next 24 hours. And this process is repeated each hour to update those programs, those 24 hours, moving like a sliding window forward in time. So this is the application of forward-looking optimization in the context of that project. Jean, in his presentation of his business case, is going to take us through some figures showing the value created by forward-looking optimization. So I'm not going to dive into this kind of information now. I'm just going to finish quickly by talking rapidly about some of the technical solutions that Energy Pool is using in terms of optimization and forecasting. So for optimization, we are using a method called mathematical programming, and in particular, mixed integer linear programming, which is very interesting in the way it is adaptable, making it possible to really adapt quite easily to different types of microgrid and different assets with different characteristics. We're using IBM Zilog Cplex as the technical solution for optimization, which is really the standard in this department. And in terms of forecasting, we do a lot of machine learning based forecasting. And to do that, we have fully integrated the complete suite of cloud-based services offered by Amazon. So that's it for me. I'll give the hand back to Jean now for his presentation of our second business case. Thank you very much.
All right, thank you very much, Nicolas, for the introduction, the transition. So I'm waiting for the control.
Do you have it?
Not yet. Okay.
Good.
It seems that it's not working. All right, so is it me who is controlling, or?
No, I'm not controlling anymore, and the thing is, I'm not asked if I should be giving the control back, so there's nothing I can do.
But when I'm asking control, it just says you cannot have the control, it has not been accepted.
All right, do it again.
Yeah, I cannot do it, apparently.
Okay, we'll do it for you.
Yeah. Okay. So so we move to the third part of this webinar, and with the presentation of the hybrid power plant. So hybrid power plant has a lot of definition. What do we call hybrid power plant at Energy Pool? Is a factory that decides to disconnect from the main grid and that is supplied by distributed energy resources, in order to increase reliability, to increase the renewable penetration, and to reduce the cost of the megawatt hour. So in this presentation, we will take the example of a factory with an average load of 5 to 6 megawatts that will be supplied by a solar PV plant of 9 megawatt peak, some battery energy storage system of 3 megawatt hour, a thermal plant of 7.5 megawatt with 3 genset of 2.5 megawatt. And of course, we will have microgrid controllers that will monitor and control all the different assets. Please, Jean-Pierre. So I will do a small technical parenthesis to introduce some key definition for the understanding. So when we are talking about power, we can talk about AC power or DC power. In AC power, the voltage has a sinusoidal form, so with a defined frequency, a peak value, some average and RMS value. And in DC power, the voltage has only an amplitude, so it's a constant value. Why am I introduce the difference between AC and DC, please, Jean-Pierre? That's because renewable power battery are producing DC power when the grid is usually using AC power. So we need something to convert from DC to AC power, and that's the so-called inverter. An inverter can operate in different modes. So when we are talking about connected mode, the power grid will impose the voltage waveform. So it will impose frequency and peak value. And the inverter will operate in the so-called grid tie or on grid. So it means that it will reproduce exactly the voltage and the peak value imposed by the power grid. When we are talking about islanding grid or islanding mode, the power grid is not anymore here to impose stability on the waveform, and it has to be shared between the distributed energy resources. In this case, the inverter should operate in the so-called grid forming or off-grid, or sometimes we also call it the emergency power supply mode, where the inverter are able to impose and to create the waveform of the voltage. So because of this, we need, so in an islanding microgrid, we need to define some operating rules, because we need to define who will create the waveform, who will impose the stability, will be responsible of the stability, since it has to be shared between the distributed energy resources. That's what we did here for our example. So we defined some operating rules that the thermal plant should operate with a minimum load ratio of 50%, except when one single genset is running. This is for a yield reason. The second one is that to ensure the stability and the inertia, so exactly for the reasons that I exposed before, the genset will will create the waveform of the voltage, so it should always take 20% of the load. It should always cover 20% of the load. For the solar PV plant, it will complete the load while respecting the genset operating rules. It means that the solar PV plant cannot cover more than 80% of the load for our case. And the power intermittencies will be compensated by the battery energy storage system ramp rate control, also calling the PV smoothing mode of the inverter. So for the battery energy storage system, during the daytime, it will do what I just mentioned, the ramp rate control of the renewable. And during the nighttime, we will use the grid forming capability to ensure the spinning reserve level. Talking about spinning reserve, so the spinning reserve in an hybrid power plant is the instantaneous reserve that all the distributed energy resources should be able to produce to face any event or to face defined event. And we defined that the spinning reserve should be enough should be sufficient to face 20% of load variation, a loss of one thermal generator, and a renewable production intermittency up to 2 megawatts. Please, Jean-Pierre. So you are a microgrid installer, you have some constraints, you have some operating rules, you have some return on investment objective, you have also some reliability objective, and you don't know exactly what kind of installation you should have, or you don't know exactly what kind of control you should have. You can call Energy Pool and we can advise you on some installation, we can advise you on the ROI analysis, we can propose you an adapted control solution, depending on your objectives, and we can do the performance analysis. So what kind of control we can propose to you? We can propose to you two different controls. The first one is called the real-time optimization. It's made by the Flexbox that Nicolas presented to you. So with the real-time optimization, we will apply the operating rules and no more, no less. It means that we will do what we call a rule-based control. So if this happens, we do this. And this rule-based control will be based on measurements. So to do this, we will do a real-time adjustment of set point to ensure, so of course, the application of the operating rules, the power quality, and the reliability. The second control that we can propose to you is the combination of this real-time optimization plus the forward-looking optimization that Nicolas presented to you. So we will add all the features that Nicolas presented, and especially the forecast of renewable production and the load consumption. With the forecast of production and consumption, we will be able to calculate the optimal spinning reserve and to allocate the spinning reserve to avoid the useless use of the genset. And the second thing that we can do with the forecast of renewable and of renewable production and load consumption is to calculate the optimal battery energy storage system profile to ensure fuel saving functionality and to reduce the part of genset without affecting stability. So let's take an example of a use case of simulation. So here in yellow, you have the load consumption, so the factory consumption. In green, you have the PV production, meaning the maximum production that PV can produce according to the weather of the day. In blue, you have the power that we use from genset. In gray, the power that we use from battery. And in orange, the power that we actually use from the PV panels. So during nighttime, we have no PV production, so the load is 100% covered by the genset. At let's say at 6, PV start to produce, so we will progressively reduce the part of the share of the genset and increase the share of the PV. And around 8 a.m., the PV production is more important than 80% of the load. So we have to curtail the PV production in order to respect the 20% of the load that should be covered by the genset. So Jean-Pierre, if you pick one time, we will see. So exactly here, we had to curtail the PV production to fit with the operating rules, because if we use more PV, we will not respect the operating rules of the genset. So it means that between 8 a.m. Please go back. It means that between 8 a.m. and 3 p.m. approximately, the difference between the orange curve and the green curve is PV production that we completely lost. So this PV we cannot use it. We actually lose this PV production. Let's now add the forward-looking optimization. So of course, during the nighttime, we still have no PV production. So the load is still covered by the genset power. And at 5 a.m., so the forward-looking optimization has the forecast that it will be a sunny day, so we will have a lot of PV production. It also receives the information from the microgrid controllers that the battery is full. So it will calculate the optimized profile and say, if at 5 a.m. the battery starts to produce, we can shut off one genset. And after this, so please click, Jean-Pierre. So we can shut off the third genset, and after this, the PV production will start, and we will use PV. That's exactly what happened. So at 6 a.m., PV start to produce, and one more time at 8 a.m., the PV production is most important at 80% of the load. But since the battery is empty, we can use the battery to avoid the curtailment of the PV. So if you click one more time, we will see it. So we use the battery to minimize the PV curtailment. So from 8 a.m. to, let's say, around 10 a.m., we use the battery to minimize the curtailment of the PV and to save some PV generation. But we use this PV generation to charge the battery without touching the operating rules of the gensets that is still covering 20% of the load. So if we have a look at the key figures of both propositions, so here in orange, you have the figures using only the real-time optimization, and in blue, you have the combination of both optimization. So what we can see on the left part of this slide is that we are using 3 hours less of genset. So this corresponds to approximately 4.6 megawatt-hour of less genset utilization. And if we only consider the fuel price and the fuel consumption, this corresponds to approximately $750 per day. Regarding solar PV production, we avoided 3.4 megawatt-hour of curtailment, so we used 3.4 megawatt-hour more of PV production, and we used 5.25 megawatt-hour more of the battery. So if we consider the fuel price and also the maintenance price, we have the key benefits of approximately $800 per day and $765 kilodollar per year. So if we summarize and if we do some remark, so some remark first regarding the cost benefits. So the cost benefits that I presented only consider the fuel maintenance, the fuel and the maintenance, sorry. So we can expect some additional saving regarding the number of start-stop of the gensets that we can include in the forward-looking optimization, and also the yield of the gensets that we can include. Regarding the battery, so you saw that we used 5.25 megawatt-hour more the battery. This is a lot. But this is something that we can enter in the forward-looking optimization. So we can add a constraint that we should reduce the number of cycles. So this is something customizable in the forward-looking optimization. And of course, the financial benefits that I presented are highly linked to the size of the battery. The more the battery is bigger, and the bigger are the benefits. And regarding the simulation, so the simulation that I presented is based on a sunny day. So we had a good or a large PV production, but we have some other scenarios available. So if I summarize, I presented one optimization based on real-time measurement and one based on real-time measurement plus the forward-looking optimization. We saw that with the forward-looking optimization, we can increase the use of the battery because we can calculate the optimized profile of the battery. We can so decrease the genset use and so the genset maintenance. We can decrease the curtailment of renewable thanks to the battery, so we can decrease the cost per megawatt hour. So that's all for me. I will give the back floor to Jean-Pierre for the very last slide of this webinar. Your mic is off, Jean-Pierre.
Sorry. Thank you, Jean. To conclude this webinar, and before we switch to the Q&A session, we would like to offer you the opportunity to evaluate the benefit of forecasting and forward-looking optimization on your existing microgrid. As we described during this presentation, we can deliver an integrated solution composed of our microgrid controller and coupled to our cloud platform. However, our cloud platform can also be connected to an existing microgrid controller with very limited technical impact. So if you have an existing microgrid, or if you are in the project of deploying an existing microgrid with only a local microgrid controller, then we invite you to, if you're interested, of course, we invite you to share with us a set of data that describe your existing microgrid configuration. We will then run simulations based on your data and send you the results, which will highlight the benefits of our forecasting and forward-looking optimization, what it can bring in terms of economic efficiency. This offer is free and is therefore it is limited to a limited number of candidates. We have put here the first 5 candidates. And we have described here the process. We have also indicated the email address to be used if you want to contact us and share the data with us. Don't bother for the initial email contact. Just say we are interested, and we will give you the details of the data we need. And we will send you again the detail on how to contact us if you're interested by an email that we will send you after the webinar. Thank you for your attention, and let's now switch to the Q&A session.
Yeah, thank you all for this presentation. You can now use the conversation, the chat window to send us your question. A question was sent before the event start, and this first question is about consumption change and how the platform, the controller would deal with a significant consumption change. Would you be able to give some answer to that?
I can start giving an answer if that's okay, and Jean or Jean-Pierre, you can.
Yeah, go ahead.
Yeah. Well, there are two levels of answer to that question, because if you're looking at the real-time optimization or control by the microgrid controller, as we said before, it embarks the logic, the rule-based logic implementing the operating philosophy of the microgrid. So those rules should include what actions to be taken in case of a sudden change in consumption or the loss of generation. So that's the first part of the answer. But if you add to this forward-looking optimization, and if this sudden change is something that was detected or forecasted, the forward-looking optimization will be able to handle this change. Of course, it's not always the case, but if it was detected by forecasts, if the information was available, then forward-looking optimization will be able to manage this sudden change in the best possible way, because it will be able to anticipate it. So I don't know if this is clear to everyone, or if someone would like to add something to this answer.
Yeah, I will just add something, is that usually, so as I presented, usually for island, because this is a subject of islanding microgrid, especially because when the renewable consumption is changing, in the case of grid-connected microgrid, we do not have a lot of problem because the main grid will cover this. But in terms of islanding microgrid, we always, or we should always define some spinning reserve. Let's say, as I explained, the spinning reserve is the instantaneous reserve that the microgrid should be able to give. And this spinning reserve, the more you have renewables, the more you will need spinning reserve to cover some renewable generation changes. So of course, this will be taken into account into the operating rules, and it will be generally covered by genset of the battery, but it will be taken into account.
Okay, we have a global question. We will of course send the PowerPoint presentation, so you can share it and review it with your colleague. Thank you. Is there any other questions regarding presentations or?
Yeah, I think there was one related to cybersecurity and cloud platform. This is a good question. Well, to answer shortly, we think that cloud is not an option anymore. You only have two options. Either you install something locally and you do not connect at all on the internet, and with that you are mostly safe. But this type of implementation have limitations now. All the utilities worldwide are now moving to cloud solutions. They were quite reluctant until I would say 10 to 5 years ago, but with the development, with the benefits that cloud solutions bring, all utilities are now moving to cloud solutions. And as a software platform provider, we of course have to go through cybersecurity questionnaire when we want to deliver our solution to utilities. So we have been through several questionnaires, several audits, and generally we meet the cybersecurity criteria of all our utility customers, small and large customers. And to give you an example of what a move that made one major utility, Enel, the Italian major utility, who is also present in the US, they moved all their private data centers to Amazon a few years ago. So all power system actors are now making a move to cloud solution, and there are solutions to secure the communication between asset and a cloud platform. But of course, this is something that needs to be integrated in the design of the solution, because cybersecurity is not a one-shot action. It is a continuous action plan that needs to be implemented to make sure that we meet the security standards. Do we have any other questions, Laura?
No, I don't see any for the moment. To date. I guess
there is a specific question on this topic. If you have questions, please contact us directly, and we will give you some more details.
Yes. Maybe you can also turn on your micro if you want to ask a question directly to a speaker. I think.
It looks like we were really clear.
Good, and we're close to the end of the time slot that was allocated, so maybe it's time for a conclusion. And thank you for the positive appreciation we just received. We hope it was it gave you some insight about some advanced capabilities that we can deliver, and do not hesitate to contact us if you want to have more information and to audit, to evaluate your existing microgrid. Thank you for your participation, and Laura, you will manage the communication in the following days regarding the sharing of the presentation. Thank you very much.
Thanks.
Thank you, everybody.
Thanks, everyone.
Thank you. Goodbye.
Bye.
Thank you. Bye.
Bye.